Welcome to our webinar, Hydrogen Innovation in Action. It's going to be an exciting webinar. We have many people on the agenda. I'm very happy to introduce Brian Mullins, who will give our official welcome. Brian is our director, our hydrogen program director, and he's overseeing the exciting job of getting hydrogen into the gas network.
Gas Networks Ireland is the transmission and distribution operator. We have a presence across Scotland, Northern Ireland, and the Republic of Ireland. We have over 720,000 customers. Our network is quite extensive. We've over 14,000 kilometres of pipeline. We've a 2.7 billion asset built over many years. And I suppose the natural gas network plays a really important role in Ireland's energy system. Roughly 45 to 50% of our power generation is coming from gas-fired power plants. And overall, about just over 30% of Ireland's total primary energy requirement is being provided through natural gas at the moment. You can see that we have 2 interconnectors to Scotland, and we have significant plans, as you'll hear hopefully later in the webinar, of opportunities to repurpose our gas network to help and deliver the hydrogen economy for Ireland. I suppose the energy conundrum that Ireland has is the fact that there are significant government targets for offshore wind. You can see the graph on the left showing the sea area that we have, which is 7 times our land. So there's a huge opportunity for Ireland to develop significant offshore. As we develop that, the issues will become around curtailment of wind and a misalignment of electricity demand and supply. Today, we curtail wind on the energy system, and we want to minimise that over time. So one of the key issues that a hydrogen economy can deliver is to take that excess renewable electricity and to convert it to hydrogen for other uses or for storage. So it's a great opportunity for Ireland to maximise its renewable generation and align the demand and supply. And of course, the third element is the fact that we've hard to decarbonise sectors. We've got the likes of shipping and aviation and heavy duty transport. These are areas which aren't suited to electrification, and hydrogen can play an important role in these sectors. So we're really looking to address 2 issues: how to tackle sectors that aren't suited to electrification, and how are we going to better align energy demand and supply such that you maximise the renewable elements of it and deliver net zero carbon in the long term. If you look at what can a hydrogen economy offer Ireland, if you look at kind of a demand supply analysis, you would say on the supply side, developing out offshore, developing more renewables and developing a hydrogen economy can maximise our renewable energy. It can create indigenous energy supplies for what is an islanded nation. It makes better alignment of energy demand and supply. And importantly, an item that's increasingly coming into the spotlight across Europe is security supply. To bring that supply to the relevant areas of demand, you need connectivity and you need route to market. And this is where we feel the existing gas network can play an important role in the development of that. Because on the demand side, you're probably going to have 4 key areas of demand from a hydrogen perspective. One is the hard to decarbonise sectors that I mentioned earlier. You got power generation optimization in terms of maximising the renewable forms and aligning where required. We're going to probably have new emerging areas of demand. Ireland imports aviation fuel, fertiliser today. These are areas where a hydrogen economy could offer the opportunity to manufacture those here in Ireland. And the other opportunity we have is export opportunities, in terms of if we develop the offshore scale, there's a huge opportunity for Ireland to export hydrogen to other jurisdictions which will need it. And what we've set out here is a vision of our network for the next 20 years in terms of how we see our network evolve to become a net zero carbon by 2045. Briefly touching on it, you can see today we have a natural gas network. We have biomethane plans. We're building a facility in Mitchelstown in North Cork for central gas injection for biomethane. And as you move from left to right here, you'll see an increasing number of green circles, which are hydrogen clusters, and connectivity between those over time. And when you get to the very right, you'll see that what our vision is to develop a twin network of completely renewable gases, no natural gas network being transported, and we have the development of a biomethane and a hydrogen network in parallel. And you can see that we will have repurposed the two interconnectors to Scotland as well to allow for import and export of hydrogen. So that's it for me in terms of a brief introduction. I'm going to pass on now to Liam Nolan. Liam is our Head of Technical Development and Technical Training here at Gas Networks Ireland. Liam oversees our Gas Innovation Fund and the Network Innovation Centre that we have in City West. So Liam's going to give us an overview of our hydrogen research. Over to you, Liam, and to everybody, I hope you enjoyed the webinar today. Thank you.
Thanks, Brian, and good morning, everyone. So, as Brian said, we're on a roadmap for a pathway for decarbonisation. We've had a conversion of gas in the past, so we've gone from town's gas to natural gas, and now we're going from natural gas to the renewable gases of biomethane and hydrogen. So to kind of achieve this ambition, we have a greater focus on innovation, and it's innovation that's going to bring us to the energy transition, the energy future that we need with hydrogen. So just in terms of our own activities in terms of innovation, we have great support from our regulator, the CRU, Commission for Regulation of Utilities, in terms of innovation funds, which we use in terms of the gas network and innovation activities related to gas network. And we also have support in terms of hydrogen activities and developing our roadmap for hydrogen. We have set up a network innovation centre in City West in Dublin, beside the Brandsbarn AGI, which at that location we have facilities for development of network-based innovation, but we also do research in terms of hydrogen, and specifically in terms of hydrogen blends at the moment, where we have appliances working on hydrogen blends, and also what we call an off-grid network, again with a blend of up to 20% hydrogen. And we also, in terms of our own process, we have a process for developing innovation ideas, generating those ideas. They come from many different sources, including within the business, our innovation partners, innovation community. And we take that through from discovery to evaluation. We do trialing and testing of innovation ideas, and then have a process for introducing those into business as usual. So we've aligned what we do with our own strategic objectives, and obviously decarbonisation is a big part of that, and also our regulators' objectives as well. And the areas that we focus on in terms of innovation are the future of gas, safety and emergency, reliability, maintenance and repair. We look at the environment and decarbonisation, future IT systems, cybersecurity, including AI, customer and shipper services, and we look at gas in transport. So I went through all this list. We have quite a portfolio of various network-based innovation projects, and also hydrogen research projects, which we're working on at the moment. And I'm going to talk through some of those in the next few slides. But one of the organizations we work with is the STVIC. So you see STVIC here is on our supply chain. And here we have David Gologly, one of our service managers, taking an award for the introduction of this new equipment, where the equipment allows us access to service lines that were previously inserted with polyethylene. They're a ductile iron pipe and gun barrel pipe, and we were able to extract a slot from the metal to allow us access to the gas service line inside. And this is one example of the network-based innovation projects that we're working on with our supply chain. Bohr. So Bohr, this is an interesting low-cost analyzer. It measures thermal and dynamic viscosity properties to allow us to infer the gas properties of the gas, including the calorific value and Moby index. And the reason why this kind of low-cost equipment is important is because we expect to have a lot of sources of gas, whether that's biomethane or hydrogen in the future, coming from lots of different areas around the country, which is very different from the top-down flows of gas that we have at the moment. So this particular equipment is on trial in our innovation centre and can measure up to 30% hydrogen in the gas. Okay, so this is just our Networks Innovation Centre. Mentioned one of the projects we're working on there is the HyGreenNet project, UCD Energy Institute, and it's looking at the operation of the distribution piping system and equipment with hydrogen. Ulster University is a great partner of ours. I won't go into the detail of this. Dr. Sheila Brennan is going to be speaking on the collaboration in this area. Another collaboration is AMBER. This is a materials research centre in Trinity College, and the picture there is the team, including a couple of our own engineers working on the project, looking at compatibility of various materials, whether they're metals or polymers or rubbers, various equipment that we have on the network and their long-term compatibility with hydrogen. Just to mention Nexus as well. So Nexus is a next generation energy system. It's an energy research program done on a national basis. We're one of the industry co-funding partners, and we've 3 targeted projects which are part of that research program, and currently hydrogen certification on the gas network and certification in Ireland more generally is the current research project with Maham Hussain working on that actively at the moment. So obviously we want to develop out our innovation centre. We obviously continue our work on network-based innovation, but also moving from blended hydrogen to 100% hydrogen and looking at energy integration aspects as well. The Strategic Innovation Fund. So we're working actively with Research Ireland on a research funding programme, which we hope to launch early in 2025. And there's 2 challenges that are central to the research programme, and that's energy systems integration and biomethane and biohydrogen production. The energy system integration really is about integrating renewable gases, including hydrogen, into the energy system at a local and building level. And the production of biomethane and biohydrogen is really looking at an increasing expanse of AD plants that are going to come in Ireland, and looking how they might contribute also to the hydrogen economy. So that's it from me. I'm going to actually hand over now to somebody that we've been working closely with for a number of years now, and that's Dr. Sheila Brennan of the HySafer Research Centre in Ulster University.
What I'm going to do is highlight some outputs from one particular project that we have ongoing at HySafer, which is looking at hydrogen and methane blends. So as Liam mentioned, I'm representing the Hydrogen Safety Engineering and Research Centre at Ulster University. I'm going to give a quick overview of the type of work we do, and then pick up on one particular project and 2 research strands within that. So at Ulster, we undertake fundamental and applied research specifically on hydrogen safety. And what I mean by that is not necessarily the material interaction, but what happens when hydrogen escapes. So where does it go? How does it spread? If it's ignited, what does it do in the event of either a fire or an explosion, and so on? We don't undertake experiments. We're an analytical and modelling team, and there's a large group of us with 12 ongoing projects. So I'm only picking up on one of these here today. We do cover everything from liquid hydrogen through to hydrogen storage tanks and so on. And we undertake fundamental research with the end goal of informing guidance documents, regulations, codes and standards, and so on. So as I mentioned, the key is hydrogen safety, but we use that knowledge in a number of different ways, both addressing technical bottlenecks, but ultimately informing guidance documents and standards, which is where some of the activities with GNI and other gas operators are going the direction of our collaboration. We do have a series of online tools as well. So when we've undertaken the fundamental research, we try and put it into a user-friendly format. So we have, for example, tools to allow you to calculate the extent of a flammable jet of hydrogen, the extent of a jet fire, and so on. But what I want to talk today is about a specific project that we have ongoing that's looking at the safety of hydrogen methane blends. So we know that hydrogen is one route to decarbonise the gas network, and the associated guidance that we currently have in place is for natural gas. So we need to understand, if we change to hydrogen, is it fit for purpose? What is needed to be amended, and so on. And we need to account hydrogen and methane are different, they have different properties. And I would always say hydrogen is no more or less safe, it's just different. And if we understand those differences, we can develop appropriate guidance with that in mind. But there's lots of different research gaps. So the project that we have ongoing, so we have an 18-month project. We have a wider team at Ulster together with 3 of the gas operators on the island of Ireland. So that's GNI, Phoenix and Mutual Energy. And our goal here is to undertake pre-normative research. So the fundamental research, but then use the outputs of that to inform safety guidance and underpin existing safety cases. And this research project there's three main directions to it, and I'm going to pick up on just two of these today, both flame stability and buried leaks. But there's so many other research gaps in this area that this really represents phase one of the activity. So I want to explain what flame stability is, to explain why we're looking at it. If you have a leak, so for example, you have a gas pipeline and you have a leak from that, if that gas leak is ignited, you can have a flame. But if it's a sufficiently small leak diameter, or the pressure of that leak is or the driving pressure is over a certain range, the flame may not be sustained. It may blow out. And this tends to happen if you have a very small leak diameter. But different fuels behave in different ways. And we need to know what's the difference when we're talking about natural gas or methane versus hydrogen. And that's one of the activities that we're looking at, because this has implications for equipment, guidance, safety cases, and so on. So just to explain the background to this, there's what we have on the left-hand side is an image of a sustained flame. What you're actually seeing is from one of our models, the temperature profile. So if you imagine a burning candle or a gas leak that where it's ignited and you maintain like a blowtorch or similar, the flame will continue to burn provided that you have a continued fuel source. So that's what the image on the furthest left shows. However, if you have a sufficiently small diameter, or depending on the pressure range, we can have a situation where that's no longer sustained. Instead, after you remove your ignition source, that flame just blows out, and instead you've got hot products that blow off downstream. And why this could be a problem is if you no longer have a flame, you can potentially have the formation of a flammable gas cloud if you're in a confined space, or you can have a sustained leak which could subsequently ignite. So just understanding this difference is important. And when we talk about flame behavior, we have something called the critical diameter, and that's the minimum diameter above which any flame will be sustained. So in the case of hydrogen, it's really small. If you have a leak diameter of 1 millimeter, which as you can imagine is really small, as long as you ignite that leak, you'll always have a flame under any conditions of pressure. But it's different for methane, and we wanted to understand those differences. As a starting point, we wanted to try and predict what that critical diameter is for hydrogen. So, and see, could we do it numerically? So we do modelling at Ulster. And what you can see on these two coloured contour plots, on the left-hand side, what we're looking at there is a leak from 2 bar pressure through 0.9 millimeters, and it's hydrogen. And as we go down through the contour plots, you can see that you don't have a sustained flame. Instead, over a period of time, as we go down through these contour plots, it's with increasing time. And on the left-hand image of the contour plots, your flame blows out. It's not sustained. On the right-hand side of these contour plots, the only difference is it's a slightly bigger diameter. It's 1 mil. And in this case, the flame is sustained. You can see after the initial image, when we first ignite the leak, it doesn't change. So what that tells us is we are able to model this behavior, and we use this to then predict flame stability for hydrogen. So that means this curve on the leftmost of my slide, what you can see on the y-axis is release pressure, and on the x-axis is diameter. And what we see in this is where that red circle is, that corresponds to 1 mil. And everything to the right of that, any leak at any pressure for any diameter above that, you'll always get a flame. If you move to the left of that, you've got a region between this curve where a flame isn't sustained and you get blow off. And that means you instead will have a leak of a flammable gas. It won't burn. So we started by seeing, could we capture this blow off versus a sustained flame? And then could we use this information to get our models to predict the hydrogen stability curve, which we successfully did. So now we know what hydrogen does. The next step was, what does methane do? And it's quite different. So it's a little bit difficult to see on these graphs here, but I'll summarize it on them. For hydrogen, we've got a critical diameter of 1 mil. So that means anytime you've got a leak through 1 millimeter hole or greater, once it's ignited, a flame will be sustained. In the case of methane, it's much larger. It's 41 mil. So I know I'm talking about small differences here, but if you imagine cracks and fittings and so on, what this is showing us, or what this work has shown, is that in scenarios where it wasn't possible to sustain a flame with natural gas, it will be possible to sustain a flame with hydrogen. So this is an example where some of our fundamental research is then, this can inform some engineering design and understanding. And we need to consider this when we're considering incident scenarios, that the behavior we encounter as we move towards hydrogen can be quite different. And the work that we're now doing, so we looked at pure hydrogen, we looked at methane, and we know that the interest is around, for example, 20%, the introduction of 20% hydrogen into the gas network. So we're predicting this critical diameter and flame stability curves for a range of blends ratios, and we hope to publish that in the new year. So this picked up on one area, which was flame stability and the work that we're doing. The next area that we're looking at is releases from buried pipelines. So if you can imagine, many of the pipelines in the distribution network and so on are buried, and they run underground. And there is a situation there where if you have a leak of the gas, it can spread, it can track through the surroundings, and we don't want that to obviously track into a building and so on. So what we're doing is we're focusing on how that gas behaves from a buried pipeline, if it is natural gas versus if it's hydrogen or it's a blend, and what is the difference. We're looking specifically at pressures where the ground isn't ruptured, it's not cratered. Instead, we're looking at as the gas disperses and spread out. And we want to understand what's the difference. So at the moment, existing guidance is there for natural gas. As we move towards hydrogen, does our flammable cloud extend? So what I mean by that is when we talk about flammable gas, we've got a lower flammability limit. So if you have 1% hydrogen in air, you can't ignite it. But as soon as you have 4% or above, you potentially can. So we're looking at the distance from the leak source to where our concentration has dropped to a safe level, with the idea that the outcome will inform safety cases. So the types of activities that we're understanding around this, or we're considering, we first looked at what you can see here is a methane leak and how it spreads out and reaches a steady state. What that blue image is the flammable cloud. So the distance from the leak hole out to when it's dropped to 5% methane in air, which is the point beyond which you wouldn't be able to ignite it. So what we're looking at in this buried leak area is how do different parameters influence dispersion. So obviously not all pipelines will be buried in the same material. They'll not all be buried at the same depth. They won't be at the same pressure. They won't all have the same leak diameter. So we're looking at how all of those different factors influence the spread of the gas. And then if we swap to hydrogen, what's the difference? And in the cases where there's a more pronounced difference, we'll look at how that varies as we increase the hydrogen percentage. So the next steps in this activity are completing the stability curves for hydrogen and methane blends. So understanding the flame behavior for different hydrogen methane mixes, and then determining how we use that information. So when we've undertaken the fundamental research, what do we do with that information? In terms of the buried leaks, we're looking at what the difference is as we move towards hydrogen. How does the material in which the pipeline is buried influence that? How does the depth of the pipeline burial influence that? So that all that information can be used to predict hazard distances. And we will be making the outcomes of this research available publicly early in 2025. And we would hope to have a webinar linked to this activity as well. I just want to acknowledge both my co-workers at Ulster who have undertaken some of this research, and also our funder at CASE. So thank you for your time this morning. I'm now going to hand over to Josh Bailey. He's a Vice Chancellor Luminate Fellow at Queen's University Belfast, and his research focuses on the implementation and optimization of ionic liquids in polymer electrolyte fuel cells.
My name's Josh Bailey. I'm a new academic at Queen's University Belfast at the School of Chemistry and Chemical Engineering, and I'm affiliated with Queen's University's Ionic Liquid Laboratories, or QUIL. And today I'm going to talk a little bit about the one research area that we're doing here, which is implementing ionic liquids in fuel cells. And really, just to give a broad overview, so I'll touch upon the hydrogen landscape, which many of you will be familiar with. And then for those of you not familiar with fuel cells necessarily, I'll give an introduction and then specifically highlight some of the technical aspects of polymer electrolyte fuel cells. And then do a little bit of a dive into the current research that's happening in my group here at Queen's, and then draw some conclusions. The hydrogen landscape is changing, and in the Republic of Ireland, there's targets for 2 gigawatts of offshore wind for green hydrogen production, as stipulated in the National Hydrogen Strategy last year. And combined with the UK Hydrogen Strategy looking for 10 gigawatts by 2030, this really represents quite an upscaling of the ambitions to produce low carbon hydrogen. But this really is looking at the generation side. And we've already heard very much about the use of hydrogen for hard to abate areas. We've heard a little bit there about safety. What I'm going to talk about today is the use of hydrogen. And in the cases of when we want to use it for energy storage, that is the conversion of that hydrogen back into electricity. So what I want to talk about is fuel cells. So fuel cells is a very broad term. As you can see here on the left-hand side, a schematic of the different types of fuel cell that really range from low temperatures of about 75 degrees Celsius, really up to about 1,000 degrees Celsius. And you can see all these different types, which are really categorized by that operation temperature, which reflects the electrolyte, different electrolytes that have different charge carrying species that you see there, really define a range of different fuel cells. But what I want to do is just really just explain the underpinnings of how a fuel cell operates. If we look on the right-hand side, we have a schematic here. If you imagine that we use hydrogen as our fuel, it comes in on the anode on the left, and at the anode we oxidize the hydrogen, which means we tear off the electrons and we separate that into protons, H+, and those electrons can't go through that electrolyte. Instead, they pass around an external circuit and they do the electrical work that we associate with getting back the electricity from the hydrogen. And on the cathode side, these electrons recombine with oxygen, so you reduce the oxygen in air to make oxide, which combines with those protons to give you the product water. So the great thing about this type of device is that it's electrochemical, not combustion. We get high electrical efficiencies of 50% or so, compared to maybe 30% for combustion. And the only byproduct in this case is water. Next. What I'd like to really highlight is that we're going to talk today about polymer electrolyte fuel cells. So that's both the low temperature type, about 75 degrees Celsius, up to 160 of the high temperature variant. So looking at polymer electrolyte fuel cells, this really focuses on using a polymer or a sort of a functional plastic in the center. So what you have here on the left-hand side is a schematic of a membrane electrode assembly, or an MEA, and that red rectangle represents the polymer. And that polymer in a traditional low temperature polymer electrolyte fuel cell, which is the most commercialized of this technology, would be found in the likes of hydrogen buses, is a perfluorinated membrane. Often it's Nafion, produced originally by DuPont, now they're spin-off Chemours. And it is a well-established technology. That membrane is then sandwiched between two catalyst layers. You can see in this schematic these sort of circles. This tends to be platinum nanoparticles on carbon materials that allow the electrochemical reactions to happen on either side. And so I'll talk a little bit about the pros and cons of that technology in a moment. But if we look on the right-hand side, we have here actually some X-ray computer tomography images taken at my previous institution in London. This is an example of a high-temperature polymer electrolyte fuel cell. If you look at the top four images, this is a pristine fuel cell that is actually not composed of Nafion and water, but instead polybenzimidazole and phosphoric acid. So by changing the materials of that membrane, you're able to operate this polymer electrolyte fuel cell at a higher temperature. But you'll see in the bottom four images that actually the phosphoric acid that's in that central membrane has escaped into the layers around the membrane. And I'll talk about this in a moment. So really to summarize, the low temperature polymer electrolyte fuel cell operates around 80 degrees Celsius, has some real advantages. It's highly efficient, there's low maintenance versus a lot of combustion technologies, and it's reasonably mature now, and it's been improving over the last few decades. But it does have some disadvantages, some drawbacks. So it does use this perfluorinated membrane, Nafion. Increasingly, there's a lot of controversy over these polyfluoroalkyl substances, PFAS, and also the operation of these fuel cells really requires ultra pure hydrogen, 99.999% hydrogen. Otherwise, often you get a carbon monoxide, for example, in your hydrogen fuel stream, and this will poison your catalyst. And certainly this limit operation at only 80 degrees Celsius because of the use of water really means that you have to use these platinum or platinum group catalysts, which are very expensive. So a lot of researchers, as I mentioned in the previous slide, focus on the high temperature variant at 160 degrees Celsius. And this allows you to move away from Nafion, a perfluorinated membrane, towards this polybenzimidazole membrane, which has better sustainable credentials. And also by going to this higher temperature, you can use other fuels and you can kind of loosen those constraints. So you can have a little bit more carbon monoxide in your stream. And these are being commercialized in some niche applications at the moment. However, as I alluded to in those images in the previous slide, there is an issue around phosphoric acid leaching. So that acid gets in the way of reactants and products. We have lower power densities versus the low temperature variant. And indeed, that phosphoric acid can poison the catalyst. So what we're really interested here at Queen's, and the technology that I'm going to talk a lot about today, is an intermediate temperature polymer electrolyte fuel cell. And this intermediate temperature polymer electrolyte fuel cell is really looking at operating point in between at 120 degrees Celsius. And again, looking to move away from perfluorinated membranes to membranes based on ionic liquids, albeit potentially with some fluorine, but certainly not to the same extent. And the idea is to still get some of those bonuses around fuel versatility by being at this higher temperature. And what I'm going to talk about today is one way of doing that is with an ion gel membrane, which can be easily synthesized in the lab and scaled up. But one of the disadvantages really is this is quite a nascent technology. It requires a lot of research and development, and yet we haven't yet seen the performance and durability proven in operating cells. So what do we need for intermediate temperature polymer electrolyte fuel cells? In this case, we're talking about the use of ionic liquids, which is a specialty here in Queen's in the ionic liquid laboratories. And an ionic liquid is essentially a compound that has ions that aren't happy to kind of combine into a crystal lattice, such that they've been designed to make a compound that is liquid at room temperature or indeed below 100 degrees Celsius. And as a result of it being ions, you have a very low vapor pressure, so you can take these up way beyond 100 degrees Celsius in many cases without a huge amount of vapor forming above the liquid. And they have low flammability and very tailored properties. What that means is we can go to these higher temperatures beyond 80 degrees Celsius, and by going to higher temperatures, we can enhance the reaction kinetics. This improves our efficiencies. We become less sensitive to that fouling by carbon monoxide that I mentioned before, and it lowers some of those costly constraints on the purity of our fuel stream, and it also simplifies our heat management. But we can also think about this from the perspective of being a dry system. So in some cases, we can retain phosphoric acid or water, or we can go for a system which is just based on liquids. And by not having that excess water, we improve water management, which is often an issue in low temperature polymer electrolyte fuel cells, because there's this issue of cathode flooding. And indeed, it can simplify the fuel system in terms of not needing to humidify the gas. Finally, some of the longer term potential impacts is that as we go to these higher temperatures, perhaps we can reduce some of the loadings of these platinum or platinum group electrocatalysts. We can produce cheaper membrane electrode assemblies, and we've got greater design freedom as we can tailor the ionic liquid cations and anions to be whatever we want in order to be able to meet our application. So what do we need to make this technology work? What's our research looking at? Well, one part of it is really looking at the material set. So ionic liquid-based materials is, as I say, a real area of excellence here. We look at the synthesis of those materials, characterizing them as we're making them, but also how we then use those materials and process them into functional components. One of the things we have to then think about is some fundamental electrochemistry. So we also look at ink formulation. So if we use some of this ionic liquid-based materials in an ink, for example, mixed with catalyst and support, we can use that ink in fundamental studies to understand how are those ionic liquid-based materials affecting the activity of the catalyst in the catalyst layer of a membrane electrode assembly. So we look at measuring mass activity so we can compare what is the performance of our novel materials versus benchmark platinum or carbon systems. But we're also very interested here in operating in real fuel cell environments, so applied electrochemistry. You can see a photo here of one of our single cell fuel cells, and interested in making sure that we have good, strong operational control in terms of the flow, the heat, and the humidity that goes into that system. Now I'd like to just dive into a little bit without going too deep into the chemistry, but just one of the research areas that we've been looking at of late is specifically making these membranes, replacing naphthalene and polybenzimidazole with an ion gel. So an ion gel is a mixture of two ionic liquid compounds. One is a polyionic liquid, which you can see at the top, pentadimer TFSI, and the other is a protionic liquid, HDimer TFO. And this is work based on some research out of Professor Maria Forsyth's group at Deakin University in Australia. And really it's looking at how we can combine these different ionic liquids so that we can make these functional membrane materials, and then later to make these into ionomers we can put into the catalyst layer. So what you see on the right hand side is these two component ion gels that can be cast from solvents at different ratios, changing the amount of protionic liquid, which is the replacement for water, versus the polyionic liquid, which is essentially your naphthalene or PBI polymer matrix. I just want to demonstrate some of the characterization capabilities that we have here within Queen's. So we have an excellent NMR suite. We just added a solid state NMR to that array, but here's just some solution NMR, which just gives you a sense of how we can characterize chemically whether or not we've made the, in this case, polyionic liquid, or indeed the protionic liquid that we're hoping to synthesize. And then we see in the middle here an example of a range of spectroscopic techniques. So here's an infrared spectroscopy, ATR, FTIR, and this can be used to look at the vibrations of the functional groups within molecules, and certainly not only understand the differences as a function of the protionic liquid content of the ion gel, but also look as a function of the spatial dimensions about the uniformity of that ion gel that we cast. And we have also a range of different thermal analysis techniques. Here's just one TGA that really is the idea of using temperature to see how the mass changes of the sample you're looking at. In this case, we're just demonstrating that actually in all cases of these ion gels that we made, we had a thermal decomposition onset of about 300 degrees Celsius, just showing that we have plenty of room in terms of the stability, thermal stability of these materials. Just to summarize this as one of the routes that we're looking at, it's a reasonably facile synthetic route, easy to make these materials and easy to cast them. We're able to make homogeneous membranes. We're also able to see that, in fact, if you go above 68% of your protionic liquid, we actually end up not having an integral membrane. So we found the kind of, for these types of materials, the upper limit of how much of this proton conductor we can put in here. But we've also identified an issue, which is that despite having these electrostatic charges holding these two components together, the leaching of that protionic liquid is maybe just still a bit too high. There's still a similar problem as seen with the phosphoric acid in the high temperature polymer electrolyte fuel cells when these come in contact with water. So this is pushing us in a direction of looking at some alternative materials for these ion gels, but also another avenue that we're exploring is actually polymerizing protionic liquids themselves and moving from a two-component to a one-component system. One thing just to touch on as well is, we look at these various different material sets, ion gels or polymerized protionic liquids, but we've also got to think about the processing. So what I'm just displaying here on the left-hand side is that we look at ink formulation, as I mentioned before, but also then taking that, using an ink spray and a compressor to actually use a stencil, a mask, to produce in-house our own catalyst layers on top of membranes. And what you see in the middle there is just an example of rudimentary membrane electrode assembly, where we can take a membrane, we can spray our catalyst layer, we can place what's called gas diffusion layers, which is helping the reactants go in and out of our fuel cell, and we can hot press that all here at Queen's University Belfast. And then finally on the right hand side we have our fuel cell, and that's so that we can actually test that in-house. So some conclusions: we need more R&D to produce affordable polymer electrolyte fuel cells. I hope I've convinced you that ionic liquid-based intermediate temperature versions are one solution. There are multiple strategies. I showed one today, but we can look at polymerizing protionic liquids for these types of materials. We really do require fundamental and applied electrochemical studies. And finally, I would really like to advocate for a holistic approach for this type of research, looking at performance, durability, as well as sustainability. The last thing I'd like to do is just highlight some of the other hydrogen innovation projects happening at Queen's University Belfast. So Dr. Paul Kavanagh is running a case-funded project on electrochemical hydrogen compression. Dr. Haresh Manyar is also leading some research on photoreforming of alcohols to produce hydrogen. And finally, Professor Chun-Fei Wu, working in carbon capture and utilization, is running a project looking at the dry reforming of methane, again, to produce hydrogen. So my final slide is just to acknowledge all of the various researchers for their support and all of the institutions here. Thank you again to GNI and Hydrogen Ireland for inviting me to talk, and thank you for listening. I'd be happy to take questions later. All that leaves me to do is to introduce the next speaker, which is Assistant Professor Andrew Phillips at the University College Dublin. He's the Irish representative of the Energy Division of UChemS. He's a synthetic inorganic organometallic chemist, and he's working on novel methods for hydrogen storage.
So I'm the project lead here at UCD. I'm supported very much by James, which you know very well at Dublin City University. And my new colleague here, Ali, is also in the School of Mechanical Engineering at UCD. And we're working with Anthony Miller here, who is the CEO of AVA Evolution, who is a drone manufacturer, which is very important for getting our technology into mobile applications. The idea is to get a decarbonized system is to generate hydrogen using an electrolyzer, and that would be using energy from wind or solar. This would be the so-called green or blue hydrogen. So this is passed to an electrolyzer, which generates hydrogen, which then has to be added to a compressor, then put into a gas storage cylinder. And then, as Josh was telling us, it has to be passed for a PM fuel cell to generate electricity, to generate a motor. And so this ideally should all be CO2 free. But in this project, we had to engage with a lot of stakeholders. And when asked about the entire process, they really identified one part that was really of concern, and that is the storage of hydrogen in these gas cylinders. When we talked to the stakeholders, they had a number of concerns here. So they were concerned about the low gravimetric density, the low volumetric density. This has important implications if you're going to put hydrogen on a mobile application. Some manufacturers were very concerned about the energy loss from the compression and the gas heating. All of them were very worried about the significant gas leakage potential, which could lead to high explosion potential. There was still some complexity with refilling and isolation. And this meant that still, if you want hydrogen to be refilled, difficult still at a station because you're going to need certified technicians. And a lot less concern now, but some older type of materials and still looking, you can see other groups are still looking at materials there with the long-term embrittlement. Okay, so to try and address this storage problem here, we thought about getting away totally from gas cylinders. And one way to do that is to go back and look chemically at compounds that are very rich in hydrogen. And other organizations, such as the US Department of Energy, have looked into this in quite detail. And they produce certain maps here. And so these maps show the hydrogen mass density versus the hydrogen volume density. Now, out of all this, you see there are different hydrides of different types of maturity. But hopefully, if you look across here, you'll see that there's one here that is of great interest, okay? And that is because it contains a lot of hydrogen per molecular weight. And that compound is called ammonia borane. And you can see here that it nicely meets the ultimate fleet targets at 2 and 3 equivalents. Now, 3 equivalents is hard to get at, but 2 and 2.5 is readily obtainable. Ammonia borane itself is a colorless solid. It's quite non-toxic. You can have it in your hands. It has good solubility in water, methanol, and organic solvents. And it's generally non-flammable at sort of moderate temperatures. Of course, like most materials, at very high temperatures, it would be. So they also produce maps here as well, which is quite important about the deabsorption temperature of hydrogen, comparing different materials, and also temperatures for release. And as you can see here, a lot of hydrides here are very exothermic when they release, and that management of the heat is quite problematic. But in ammonia borane, you're quite thermally neutral here. So you're not requiring too much heat for the environment, but you're not releasing too much heat. So that lends itself very well for catalytic dehydrogenation. Okay, so if we look at some characteristics here, if we are looking at a comparison against a 30 kilowatt ion battery here, we see that the battery itself, as most people know, would be quite heavy. It's quite large in volume. And looking at a class 1 compressed hydrogen cylinder there, a lot less weight, but more volume. So if we look at the energy equivalence of ammonium borane, we see that this is quite favorable. We need less weight, but also significantly less volume. If we look at our diamino borane, which just gives off one hydrogen as well, a little bit more weight than hydrogen, but significantly less volume. So already from a mobile application, the use of ammonium borane looks quite favorable. What I'm going to step through with you here is the total cycle here. And that's very important if you want to make a sustainable process here. So we've been working on all aspects as showing here on the left side. And I'm going to step through for you first upon the left side here on the onboard dehydrogenation. Okay, so that all starts off with having the right chemistry. And we spent a number of years here on catalyst development here to try and come up with a system that would efficiently dehydrogenate ammonia borane. So this is pretty important because I'm going to introduce a new concept to you. So rather than storing hydrogen, what this catalyst on contact with ammonia borane generates what I call transient hydrogen. So you're only generating the hydrogen that you need to pass to a fuel cell, and the fuel cell consumes it. So you're not generating huge volumes of hydrogen, you're just generating what you need, and then it's consumed. So I'm going to talk in a second here about the reactor design, because that's quite important. But as you can see on the left side here, we basically pump the solution into a reactor where the catalyst is. The catalyst generates high purity hydrogen, as I will show you, to a PM fuel cell. And then we will take then the spent AB and reprocess it off board. Okay, so a little bit about the catalyst. I spent many years in catalyst design, and I was quite fortunate in the areas that I worked with to come across a bifunctional catalyst. So we looked at this from many points of view in terms of computational chemistry. And a bifunctional catalyst is unique in that the metal and the ligand, where usually the ligand is inert, they are involved in the dehydrogenation process. That makes the dehydrogenation extremely efficient. And so the catalyst itself picks off a equivalent hydride and proton from ammonia borane, and then recombines that to give you your gas here. And you can see from this slide here that the efficiency of the catalyst is really quite high. And at the end, we're getting close to the 2.5 equivalents. So we went ahead and we did 2 generations of patent here, and there are some publications as well. Okay, so just to show you as well that we are generating very pure hydrogen without the formation of hydrogen here. We only have a little bit of oxygen and nitrogen that comes from the atmospheric loading. And right now we can establish it's 99.99%. We are having other equipment come in that will establish it to 4 decimal places here and preclude any ammonia being generated, because obviously ammonia borane could have the potential, but we've never seen it. And importantly, we've never killed a PM fuel cell using this technology. So we're pretty convinced of the purity of hydrogen coming out of this system. You might think that taking a benchtop concept that was run by a number of postdocs and postgraduates over years was an extremely simple process to move that to a self-contained reactor. But let me assure you that was not the case, okay? Integrating the 2 systems there took a lot of effort, took a lot of thinking here. And we couldn't just pump in the ammonia borane, just a whole sort of it, and just have it generated. In fact, we had to be a bit more conscious about how we fed in the ammonia borane into our system here. So we spent a long time to try and design a system here, and it's gone through many generations. But we found that incorporating an Arduino microcontroller here was really important. And with this as well is an array of sensors that help to understand the flow rate and the pressure generated by the catalyst on contact with the ammonia borane. Okay, so this Arduino system is also hooked up for the pump. And we found that by monitoring the flow and pressure, we could understand the behavior of the catalyst better and be more adaptive to making this idea of transient hydrogen. So as you can see here, we have tank A that is connected to a pump B. B is connected to the Arduino system there, and that pumps the ammonia borane into container C there that contains the catalyst. Okay, we also have a graphite filter to ensure that there's no other impurities, but that's just a safety protocol there. And it gets into G and H, which are sensors, which then basically then feed it on to a fuel cell J. We also, if there's any hydrogen that's produced, is recircled back into the system here. So we're really working on the concept of capturing all the hydrogen and making sure that's processed by the fuel cell. And you can see here, very importantly, that we use the pulse system. So we're only giving the amount of AB required to produce a very steady PM output there. So we're quite happy with that. We're just working now on reducing the system usage. So very important was the off-board regeneration, which we've just recently had some great success with. Okay, what we've shown here is we can take the AB, we can dehydrogenate it with our catalyst, we get our polyborazolene here, but importantly, could use a safe catalyst to metallize the compound to get this quite sublimable type of material, and then using a reductant, in this case lithium hydride, we generate the ammonia borane. You can see the two NMR peaks there showing the exact material coming back here. And we could do that at the moment in 60 to 70% yield. We've got a number of applications that are possible with this, including backup power supply, long-haul trucks, drones, and this also creates a possibility of large-scale bunkering. Okay, so this is our Resor team here. We've got engineers, we've got technical economic modelers, we have people working on the regeneration, we have people working on the reactor. So it's a very, very good, very fluid team that's able to work and come up and solve many problems. I thank SFI, or now what is known as Research Ireland, very much for funding under this National Challenge project. With that, I will pass it on now to Katrina Elderman, who is a sustainable professor at the University of Edinburgh, who's going to talk about underground hydrogen storage for Ireland.
So today I'm going to take you on a short journey through the underground hydrogen storage opportunities for Ireland. So we're going to look at some of the scales of energy storage we're going to need to achieve net zero. We're going to look at the underground hydrogen storage technologies under consideration. And then I'm going to present some of the technical considerations for hydrogen storage in depleted gas fields that the wonderful subsurface team at Edinburgh University have investigated. So we all are aware of the critical role hydrogen is going to play in supporting net zero, both in supporting that increased renewable energy sector by providing large-scale energy storage to balance supply and demand, reduce renewable energy wastage through curtailment, support grid resilience, and provide energy security. And then secondly, in that decarbonisation of sectors that are difficult to electrify, such as shipping and aviation and industrial processes. But one of the things I think is really interesting as a geologist, which is my background, is also that if we consider hydrogen generation from the reformation of hydrocarbons with carbon capture and storage, then of course that cost of carbon storage is included in the cost of the hydrogen production. So finally, we may have an economic case that will support the development of that wider CCUS industry. So hydrogen is a real enabler for a wide range of decarbonisation technologies. So for this talk, I really want to specifically focus on hydrogen energy storage, for this is the key to unlocking that fully renewable energy system and achieving our net zero targets. So the figure on screen illustrates how hydrogen can support these different sectors and provide energy storage across various timescales and needs that each of these sectors will have. So on the left of the figure, you can see the sectors requiring decarbonised energy. So that includes electricity, industry, transport, heating, and of course, energy security. And then on the right, we have the storage solutions, and these are categorized by timescale. So we have short-term storage for, say, grid balancing or load shifting. We have medium-term storage for covering, say, maintenance or price arbitrage. We have long-term storage covering energy contingencies or Dankelflouts if the winds aren't blowing. And then, of course, we have the seasonal storage for winter heating. So this figure, I think, really demonstrates that full range of capacity and flexibility that we're going to need from our hydrogen energy storage technologies that we currently have in our existing system and can be delivered through hydrogen. So this slide shows you the hydrogen storage requirements for 2050 for Ireland from the National Hydrogen Strategy. It covers both those 14 days and 90 days of storage. It's categorized into domestic gas energy storage, which will require interseasonal flexibility, and then the industrial hydrogen derivative needs, which will require a more constant or perhaps maybe weekly or daily fluctuating storage flexibility. And what you can see here is that for 14 days of storage, your total storage requirements will range, these two different scenarios, will range from 0.8 terawatt hours to 2.9 terawatt hours per year. For 90 days, this grows significantly, with the total of storage needs ranging from 4.9 terawatt hours to 18.4 terawatt hours. And what is the recognition in the National Hydrogen Strategy is that there's really a recognition that large-scale geological hydrogen storage will be required to meet these energy demands. So this slide is really quite an important one that I want to talk through. So it outlines really the various energy storage options categorized by system power and discharge duration. So at the lower end in grey, we have the existing short duration energy storage solutions. So we have our pumped hydro, we have our batteries, really important for that fast response energy storage. But as we move to a more renewable based energy system, we're going to require these longer term, higher duration, higher power storage options. And at the moment, really the only options are available are in geological hydrogen storage. You have large capacities in the subsurface, and that's really what this takes advantage of. So if we think about those smaller scale ones, we've got dedicated storage in pipelines or silos or subsurface tanks. But moving up, we're looking at storage in lined rock caverns and then ultimately into salt caverns and porous rock formations. And these are really the only technologies that are capable of providing that weeks to months worth of storage at that gigawatt to terawatt hour scale that we're going to need. So really the key takeaway from this image is that geological storage is really important to deliver that required sort of scale of energy storage with those discharge times that we're going to need. And of course, if we focus back in on Ireland and its anticipated storage requirement of 18.4 terawatt hours, then we really do see that porous rock storage is going to be really important. And of course, a key mechanism of that, which is a really exciting project, is the Green Hydrogen at Kinsale project, launched by ESB and Decarbonex. So this is looking at repurposing the depleted Kinsale Head gas field and then converting it to a site capable for storing up to 3 terawatt hours of green hydrogen. So a very important kind of asset, storage asset within to support Ireland's hydrogen ambitions. So then you ask, well, have we done this before? Have we got experience in storing hydrogen in the subsurface? And the answer is absolutely, yes, we do. So what this slide does is highlights the worldwide experience in underground hydrogen storage, demonstrating both that it's commercially and technically feasible. Several hydrogen storage technologies are already in practice. We've been commercially storing pure hydrogen in salt caverns in Teesside and in the US since the 70s. So these have been operational for over 50 years. During the 50s, 60s and 70s, there was the commercial storage of town gas. We already heard about the transition we went through before. And of course, town gas was over 50% hydrogen in its composition. And that was stored commercially in porous aquifers, so deep subsurface aquifers, for decades. And many of those have been repurposed now to natural gas without any consequences. We have two very specific pilot projects currently injecting hydrogen into depleted gas fields through the high storage project in Bavaria with Uniper and the RAG underground sun storage in Austria. So these are really important pilot studies for us. And then finally, we have the Swedish HYBRIT project. So they don't have any salt caverns, they have hard rock. So they've developed a lined rock cavern for hydrogen storage to support their decarbonised steel manufacturing. And they've successfully excavated and gas tight tested that site with hydrogen and are now ready to upscale that. So all of these projects are really important in developing that evidence base to demonstrate the feasibility of geological storage of hydrogen. So there really is a huge range of pilot projects underway. I always think it's worth reminding ourselves that, it was only in 2018 that the Committee for Climate Change kind of recognised that role that hydrogen could play in achieving net zero and recognising its importance. So all of this has literally happened within the last 5 years. So there's a huge range of pilot projects underway now for hydrogen storage, or certainly large-scale hydrogen storage. So the map that you can see on screen is a snapshot of just some of these projects. So not all of them are operational yet, but they're certainly all in planning or under consideration. So on the map, you can see that salt cavern storage projects, so these will be hydrogen storage testing in solution mined salt caverns. They're shown in the blue dots. The porous rock storage projects are shown as the orange dots, and that of course includes green hydrogen at Kinsale. And then the lined rock cavern projects are shown by the grey dots. So these are the technologies that are available to us for geological storage of hydrogen. So let's move on to some of the geological considerations for hydrogen storage in porous rocks. This is going to be the technology that's really required to deliver that capacity that will support Ireland's hydrogen storage requirements and ties into the the projects that are already being looked at for feasibility studies. So because this was really a relatively new research field at Edinburgh, we began by just addressing those overarching critical questions. So we started this work back in 2018 or even prior to that. But what we wanted to do was, what is going to be the showstoppers? What's going to cause the biggest problems? We need to start from the top down and say, is there anything that's going to happen that's just going to kill this as a technology? So those really are there going to be any chemical or microbial reactions that could damage or compromise the integrity of the storage site and the wells? Can we recover all the hydrogen that we inject into the reservoir back and forth over these multiple injection cycles that we'll need for these operations? And then how do we manage and optimize our subsurface operations? So those were really the key kind of big or first order questions that we wanted to look at through our research. So let's start with the geochemical reactions first. Hydrogen is known to be a strong reducing agent. For example, sulfate ions within reservoir minerals could be reduced to form hydrogen sulfide, which we definitely don't want because that can increase the risk of infrastructure corrosion. So we have tested hundreds of different rock types, and the results always indicate that there's minimal risk from geochemical reactivity with hydrogen across most of the materials tested, which is really great news. It's not so good news if you're an academic and you're trying to publish because nothing happens, but we keep saying this is good news. No news is good news. What we did find was there's one small exception, and that's when pyrite, which is an iron sulfide mineral, and we did see some reactions with hydrogen at temperatures above 100 degrees centigrade, and that did lead to the release of hydrogen sulfide. But we can mitigate this risk by understanding where the pyrite is distributed within our reservoirs, or targeting storage formations with rocks that have minimal pyrite. So we can manage these risks very effectively. They're not going to cause any kind of purity issues or degradation in the reservoir. So another thing we wanted to think about, is particularly when we're looking at depleted gas fields, is the fact that there's already infrastructure there. There's already a number of wells in these reservoirs. So they could pose a leakage risk in underground hydrogen storage operations. So we did some experimental testing of the well cement, similar to we did with the rocks, the rock minerals. And again, we didn't see any significant geochemical or structural alterations to the wellbore cements on exposure to hydrogen. Again, good news. Of course, the legacy wells may be a concern. More wells in a field equate to a higher potential for leakage. So the figure on the screen shows the UK continental shelf depleted gas fields. Sorry, I don't have any of the Irish ones, shaded by the number of wells. So the darkest purple reflects the highest number of wells. And it's no surprise that the largest fields have the most wells. So I guess that then kind of instigates the question that maybe more smaller fields with less wells may be more favourable when managing underground hydrogen storage than a very large field with multiple with many wells, because the cost might be just too much. But these are some of the investigations that are ongoing. So bugs. Subsurface is teeming with microbes, and their absolutely favourite food is hydrogen. There's 4 main types of bacteria that will consume hydrogen. We have the methanogens, which consume hydrogen and produce methane. We have homoaccogens, which will produce acetate. We have sulfur species reducing microbes that will consume hydrogen and produce hydrogen sulfide. And then we have the disseminatory iron-reducing bacteria, which can transform iron into a solid phase, blocking up our pore networks. It is something that we want to keep an eye on. But microbial activity is highly sensitive to temperature and salinity. So we looked at the life limits of the 4 main hydrogen-consuming microbial communities and found that at temperatures above 122 degrees and high salinities, they were unfavourable to the survival of these metabolic activity. So using temperature and salinity limits established for microbial activity, we developed a risk-based screening to assess the potential for hydrogen-consuming microbial activity, again in the UK's fields. And most fields can be considered at low risk, with only 9 fields considered high risk from microbial consumption. What I think is particularly relevant for your Irish offshore basins is that many of the fields were at previously greater burial depths and as such higher temperatures. So there's likely to be paleo-sterilisation of these microbial communities in these fields. And there's an amazing work being done at the team at Trinity College that are suggesting that we do have paleo-sterilisation there. So we've established that geochemical risks might be minimal, well leakage and microbial risks can be managed. We now need to understand geological controls on the efficiency of hydrogen storage operations. So we did some work with CGG to develop a reservoir model to evaluate the impact of reservoir quality on hydrogen storage operations. And reservoir quality is really defined by the storage capacity, which is the porosity, the amount of capacity it can hold, and the ease at which the hydrogen can flow through the reservoir rocks, or its permeability. And for this study, we looked at 3 different rock types with 3 different reservoir qualities that we modelled to evaluate the impact of that quality on hydrogen storage with a simple domal structure, with a hydrogen working gas and a cushion gas that's required to manage the reservoir pressure to allow hydrogen working gas injection and production. And the picture of that system is shown on screen. So the graph on screen that you can see shows the results of gas production and injection against time. Time is divided into 3 phases: the cushion gas injection, then the hydrogen working gas injection, and then the hydrogen working gas production. And unsurprisingly, good quality reservoirs facilitate the best hydrogen working gas injection and production. But there's not a huge difference in production and injection with moderate quality reservoirs, which is encouraging. Poor reservoirs do exhibit a significant reduction on hydrogen working gas injection and production, so probably best avoided. So for the last slide, I just wanted to kind of highlight the idea for anyone who's looking at the the transition of the oil and gas industry, because many producing fields are nearing the end of their production lifespan. And that, I think, raises an important question. Should fields that are ideally suited for hydrogen storage be depleted below the pressure needed to provide that effective cushion gas, a cushion gas tipping point, as it were? Because once it drops below this threshold, converting it back to an operational hydrogen storage site will require the purchase and re-injection of additional cushion gas, which could be an additional cost that you don't need. I hope that I've given you some insights and confidence in the underground hydrogen storage opportunities for Ireland. I'm looking forward to answering any questions that you have. I'd like to acknowledge the funding that has supported our work at Edinburgh University and thank GNI and Hydrogen Ireland for the invitation to speak at this webinar. I found it fascinating. I will now hand over to Dr. Ahmed Rafi, who is a Senior Research Fellow at the University of Galway, and he works examining the prospects for green hydrogen-based decarbonisation of high-temperature heat and chemical feedstock in Ireland. So Ahmed, the floor is yours.
I'm glad to be here, and the title of this presentation is the potential role of the Irish gas grid to transport hydrogen in the decarbonized energy system. So the background is gas is currently the primary source of power production, and 50% of the annual electricity generation in the Republic of Ireland is from gas, and 67% of the gas consumption occurs on the high pressure transmission network. The existing gas network is compatible with 20% of hydrogen mixing, and the hydrogen mixing will deliver a partial gas decarbonization. And state-of-the-art power to gas and hydrogen injection into gas grid received much attention in recent years. Several projects on hydrogen injection onto the gas grid are operational or under construction, and literature is rich on simulation optimization of gas and electricity networks with power to gas. And green hydrogen injection to the Irish gas network has been studied to calculate operational variables and parameters. So there is a lack of research on sizing of hydrogen supply chain for grid injection. So a proposal has been recently finalized with GNI to conduct a study on this topic. So the objectives of this study are to construct a techno-economic model, set out a number of scenarios, determine the hydrogen mixing level based on the electricity source, examine the effect of hydrogen storage on the levelized cost of hydrogen, and investigate the impact of dedicated wind farms on the levelized cost of hydrogen. So the scenarios considered here are shown in this table. We have considered several parameters such as hydrogen storage points, hydrogen injection location, electricity source, electricity price, which is a function of the electricity source, and storage types. Three different or compressed gas tank, liquid hydrogen, and underground storage. The first scenario, the hydrogen storage points are in Carib. The hydrogen injection is in Belonnaboy, and the electricity source is curtailed electricity with the electricity price of 0, and the storage type are compressed gas, liquid hydrogen, and underground storage. For the next three scenarios, the hydrogen storage point is in Poolbeg. Hydrogen injection occurs in Dublin North, and electricity source is again curtailed electricity, and the storage types are the same as the first three scenarios. And for the last three scenarios, here the hydrogen storage points is in Kinsale, injection location is Middleton, and curtailed electricity is the electricity source, and the storage types are the same as above. The next three are combination of all of the above hydrogen storage point and injection locations, and for this, the same storage types are considered. There are two other scenarios that I consider this hydrogen storage in Larne in Northern Ireland, and hydrogen injection occurs in Island Mackey, and the electricity source is again curtailed electricity, and the last three are the same as the first three with Corrib storage point, but the electricity source is a curtailed electricity and 200 megawatt wind farm considered to do the analysis, and the electricity price of this electricity that comes from this wind farm is €46 per megawatt hour. Material and methods, an Excel-based techno-economic tool is used to do the analysis. The inputs of the tool are hourly wind and solar electricity price data, hourly hydrogen demand over full day, storage types, which are compressed tank, liquid hydrogen, and underground storage. And the outputs are hydrogen capacity factor of electrolyzer, size of main equipment, and the levelized cost of hydrogen for the whole supply chain, and model and assumptions. So we have considered different the elements in this analysis for the CapEx and OpEx. For the CapEx, we have electrolyzer, compressor, storage, and energy management, interconnection, engineering, decommissioning. And for OpEx, we have electricity, electrolyzer, compressor, storage, and water. And the construction of the project is 1 year, operation is 20 years, and decommissioning is 1 year. And the references to this data are given in this table. So this map shows the Irish transmission gas network. That gas is currently supplied at two different points. One comes from the UK gas interconnector, and the other one from the Corrib gas field. And this map also shows the location of the power plants. So the inputs to the model are collected from different sources. For example, the 2021 electricity demand, wind and solar production with 15-minute time resolution is collected from reference 6. And this table also shows the electricity demand data for Republic of Ireland and Northern Ireland for 2021 and 2030. We have installed wind, installed solar, and also Corrib gas supply in different years for Republic of Ireland and Northern Ireland, and also the gas supply from Moffat is also shown in this table as well. And for this analysis, the hourly 2021 wind and solar availability were scaled up to get the 2030 profile. The hourly 2021 electricity demand data were scaled up to get the 2030 demand data, and the electricity curtailment at any time of 2030 is the renewable electricity availability minus the electricity demand, and the hourly gas supply data in 2021 were scaled down to get the gas supply data in 2030. And this graph shows the scaled up profiles of the electricity demand and total renewable generation for Republic of Ireland in 2030. Similarly, this graph also shows the scaled up profile for Northern Ireland and also for Northern Ireland in 2030, which are electricity demand and total renewable generation are shown here. And the results, this figure shows the storage site for for different scenarios that was shown in previous slide. And you can see for the quality, the required storage size is 2.7 kilotons. For Dublin, we need a storage size of 14 to about 15 kilotons for Dublin. For Cork, we need about 6.7 to 6.9 kilotons of hydrogen storage. And when we consider a combination of the previous three cases, the storage size increases to 16 to about 16.9 to 17. And for the LARN, the storage size of these scenarios are about 3 kilotons. And for Corrib, when you consider a dedicated wind farm, the storage size reduces to about 0.9 kilotons. And this figure also shows the total capex and capex breakdown of the different scenarios considered in this study. As you can see, the cases where we have compressed gas hydrogen storage, the share of capex is about 80% of the total. And also, as you can see, in some of the scenarios, the total capex can be about 8 billion euros. And in another scenario, the share of electrolyzer capex varies between 40 to 55%. And this figure shows this the electrolyzer size and also the capacity factor of different scenarios. As you can see, for the first three scenarios, the electrolyzer size is 270 megawatt. For Dublin is about 1800 to 20,000 to 2000 megawatt. For Cork is 770. For the scenario that we consider a combination of different storage location, the electrolyzer size is 2030 megawatt. For LARN is 1000, and for Corrib with the dedicated wind farm, the electrolyzer size reduces from 270 to about 80 to 90 megawatt. And the right hand side, you can see the electrolyzer capacity factor, and use of this dedicated wind farm increases the capacity factor to about 70 to 80%. And this figure shows the levelized cost of hydrogen breakdown of different scenarios. As you can see, for the cases with compressed gas hydrogen storage, we can see that the levelized cost is about 14 to 15, more than 14 euro per kilogram of hydrogen. And the scenarios with Corrib with dedicated wind farm, we can see that levelized cost of hydrogen reduces from, for example, about 15 to about 7.5 euro per kilowatt for the compressed gas hydrogen storage. And for these cases, the cases with the compressed gas energy storage, the storage has the highest share in the levelized cost of hydrogen. Yeah, and this table shows the scenario table with the outputs of this, the outputs of the techno-economic tool. So the conclusion is that the amount of hydrogen required for 20% mixing is about 120 kilotons. The Cartel Electric can provide a maximum 10% of mixing to the imported gas, and hydrogen storage in compressed tanks results in high levelized cost of levelized cost of hydrogen, with share of storage capex of 60 to 70%, and levelized cost of hydrogen of scenario with liquid or underground hydrogen storage is in the range of 2.2 to 3.5 euro per kilogram. And the use of dedicated wind farm can reduce the size of electrolyzer and storage by about 70%. So the future is to use dedicated wind farm for other scenarios 2A to 5B, evaluate the potential of hydrogen export via repurposed or dedicated pipelines, and reduce the ownership for 2050 scenarios, excluding the residential and commercial sectors from the grid. Thank you very much.
Hello everyone, I'm Ali Khtiari and working just on as a secondment, working from secondment from Gas Island to NSAO, working on standards to update the natural gas and overall gas standards to be adaptable for hydrogen use. This is the main scope of and goal of my role in NSAI at the moment. So transferring all previous skills to NSAI, and also as presenters today mentioned about like their initiatives and research projects, so we can just use them in the real world to update our standards gas. Today I will just, conscious of time, 10 minutes, I think I try to finish, just give you an update about like what progress we have regarding hydrogen standards, and also I will introduce the gas technical committees here in NSAI, and also I will focus on just the international level updates regarding hydrogen standards and the technical committees that we have at the moment. And two main questions, as Leon mentioned, about the town gas, and then we switched to natural gas from town gas hydrogen to natural gas, and now we are switching back to hydrogen again. So we have a huge potential of like infrastructure, gas infrastructure here to use hydrogen. The two questions, the technical questions. First of all, what are the end users limits and equipment limits, and how we can just use this huge infrastructure that we have for natural gas to be adaptable for hydrogen use. So just here in NSAI, I will give you an introduction about like NSAI and the standards and the committees that we are working dynamically and with them. So in the international level, so we have ISO IEC, which is focusing on electrotechnical standards, and also ITU, and in the European level, we are actively working with the CEN and CEN-ELEC, and also ETSI, which is telecommunication standards. And then in the national scale, we have National Standards Authority of Ireland, Standards Authority of Ireland, and ICT industry. In the hydrogen, just the segments, in the context of hydrogen, we are working with the CEN in the European level, and to just work on just updating the standards regarding hydrogen and natural gas. We have 10 different categories in NSAI, which is hydrogen would fall under energy, environment, and utility category or sector here in NSAI. So we have different categories in NSAI. I'm working in energy, environment, and utility standards. So the main purpose of our work here in NSAI is just make sure that our customers are satisfied at the end of the day. As our researcher and presenters mentioned about the safety, like Sheila presented about safety concerns, and also our project in the Network Innovation Center. So the first priority is the customer safety, and then so we have different categories and different sections that we are focusing at the moment, like leakage and gas detection equipment, and metering system, and how we can meter and measure the flow rates of hydrogen in the mass term or volumetric terms, and hydrogen quality in terms of the energy quality and energy value of the gas mixture, hydrogen blends, or pure hydrogen, and finally compatibility and certification for existing equipment. If you click on just the slides, before just clicking go to the next slide, you can see here just on the very right hand side, two gas hubs flames here. Just we have 20% hydrogen blends. One of them is 20% hydrogen blends at the bottom, and also the other one is natural gas. Just visually, we cannot distinguish between these two type of gas. If you click on the slides, you can later on try on to see which one you just try to guess. It is one of the results from our experiments in the Network Innovation Center. I wanted to show you here, the purpose is to show you that there is no difference visually, but from the technical point of view, we need to be focused, and we narrow down our studies in the practical way to make sure that hydrogen is ready to be used with our end users. So the priority here in NSAI, safety, gas quality, underground storage, power generation, industrial steel pipeline in the distribution and transmission pipeline systems, and also the gas quality requirement for our industry, our end users, how much much gas caloric value they need to be to use, and how we can just supply this gas for them using hydrogen. This is main priority in European Commissions, in European committees for standardization and the CEN, and also GERG as a research institute, just which working on the research projects. To support these priorities and the scopes in NSAI and the European level and international levels, because we are interconnected network, gas networks. So in NSAI, in National Standards of Ireland, we have gas technical standards committees, and which is working for more than 30 years, about like 40 years. But since hydrogen comes as an alternative option as an alternative option to be used in energy systems, we have different technical committees here to be focused on how hydrogen can be used in our energy systems. And then, so what standards are related to hydrogen, and how we can just update them and upgrade the standards, amend them, revise them. So, for example, TC1, gas distribution pipelines systems, this TC5 is for technical committee, TC stands for technical committee, TC5 gas transmission, TC8 for LPG and LNG installations, TC6 related directly to the hydrogen use of gaseous fuel in vehicles, which is we are working on updating the standards, ISO standards, and also European standards, TC11 gas quality, and we have subcommittees as well, which is focusing more specifically on hydrogen. We have 3 working groups, working group 1, 2, 3, which is I'm inviting you to join to our working groups, to our technical committees, so and help us to upgrade and speed up the upgrading the standards, national standards to be used for hydrogen. Hydrogen coordination groups, hydrogen quality requirements, and hydrogen academic and research and academic groups. So you are very welcome to join our technical committees, and then by joining our committees, you will have access to all like documents and standards, and you can just actively working on standards and joining to our meetings and like discussions to see how we can just expedite this process. Just I summarize here the standards related to hydrogen: the gas infrastructure, safety, storage, transport, and material compatibility. One important message, and I want to update today meeting, is just European Committee for Standardization, CEN, recently established a new coordination group for hydrogen in different categories. Hydrogen coordination group established for just focusing on production, transmission and distribution, industry, mobility, energy, and building. These are the main categories of this group in European level. So we are collecting and also technical committees in different technical committees in CEN to see what standards are needed to be updated as soon as possible for our end users. Focusing on our end users is the main scope of this coordination group, to satisfy them. For example, some of our end users, they want to use hydrogen in downstream sites. Some of our other end users as a supplier, they want to use hydrogen as a product. So because of that, we have these categorized, and also this coordination group, which is leading by Dean in Germany, Berlin. Our next meeting is next week, so we are going there to see to update our technical committees, and so to see what role we can play there to update and upgrade as soon as possible the standards. I will give you a report later on related to this coordination group if you are interested. At the end of my presentation, you have my email, my NSAI email, and also my GNI email can be shared with you. So you are very welcome to contact me directly. And so if you are interested, join our technical committees. Just to give you an update, what we are doing now in NSAI and what we have done so far. So the good news is for Irish Standards 329 is for gas distribution mains natural gas. So we finished the amending these standards for pure hydrogen, 100% hydrogen use in distribution pipelines. So it's really at the moment we are working with our editorial departments to edit the final versions, and then we will circulate within just internal technical committees to get the final approval. Then hopefully by in new year, in next year, the first quarter, we can just finalize the first draft, and then hopefully in 2025 you will have IS 329 to be used for 100% hydrogen distribution pipelines. Then at the moment we are working on IS 3228 gas transmissions, high pressure pipelines. So it's very hard work because this is the pure hydrogen, the high pressure operating pressure, so it's a bit need more work. So also we have I have reactivated TC74 Technical Committee 74, which is for hydrogen production and storage technologies, and also as I mentioned about the TC1 academic research working groups, and TC6 in NSAI, and sub working group 5 for fuel cells and hydrogen use in vehicles, fuel stations, and also 76 is for biomethane, 75 for carbon capture, transportation, and storage. You are very welcome to join these committees. If you have any questions, the technical questions, you can ask, you can share your question in national level and also international scales and levels, and then we will try to answer them. And you can just help us if you have knowledge or experience related to hydrogen or natural gas. You can help us to review our standards here in different technical committees. And for register your interest in our in our technical committees, I put the links there, so you can click on them, fill the form easily there, mention the technical committees that you are interested in to join. Then I will approve your application hopefully, and then you will have access to our platform, NSAI and European platform, to work on it. Just I put here just a kind of like optimistic and good news come out from our last research project in high end in the Network Innovation Center. You can see 90% of our end users are capable to use up to 20% hydrogen, even in the large industry units, and only 10% are not capable to take up to 20, just up to 5% hydrogen blends maybe. To say that how much our end users are interested in use to switch to hydrogen, renewable hydrogen, or renewable gas in general, or renewable gas mixture like biomethane plus hydrogen. So it's important to speed up this process in real world as well, beside the progress in the research area. So it's important use as a study in industry and the standardization of hydrogen. There are some useful links that you can just click on them and read, and our previous and last published reports. And thank you so much.
Thank you very much for all the contributors today and questions, and for your attendance here. Thank you very much.